Dear students, welcome to a class of topology. Today we are going to discuss some equivalent conditions of base for a topology. Okay, we will start the theorem. Theorem says that let script B be a collection of subsets of capital X which covers X. Then the following are equivalent. Then the following conditions are equivalent. Following are equivalent. Okay, let's see what are the conditions. First statement says that since X is a set, there exists a topology. We can consider a topology. We can get a topology. There exists a topology to on X with B as base. Script B as base. Second condition says if you given some B1 comma B2 in this collection, if you have two sets in this collection, then you consider their intersection B1 intersection B2. This is again a set, correct, which will be clearly a subset of capital X because B1 and B2 are subsets of X. This subset can be expressed as union of members of B again. Union of members of B again. And the third statement says that if B1 comma B2 are two elements in script B and you take X as an element in their intersection B1 intersection B2, then the statement says that there exists some B3 in script B such that X will belongs to B3 and that B3 is contained in B1 intersection B2. Okay. So what it says, when you have a topological space X store and when you have a set X, not a topological space, when you have a set X and a collection script B. What is a collection? This collection consists of only subsets of X which can cover X. It is like that. Some subsets of capital X all together can union of all these kinds of sets will include X itself. That is the meaning of X covers X. ഇവരുടെ യൂണിയൻ ഉപയോഗിച്ച് നമുക്ക് എക്സിനെ മുഴുവനായിട്ട് കവർ ചെയ്യാൻ പറ്റുക. ഐ മീൻ അതിലെ എലമെൻസുകൾ എല്ലാവരെയും നമുക്ക് ഇവരുടെ യൂണിയൻ ഉപയോഗിച്ച് ഉണ്ടാക്കാൻ പറ്റുക. ഓക്കെ, ഇതാണ് നമ്മുടെ കളക്ഷൻ തന്നിട്ടുള്ളത്. Now what are the statements says? There exists a topology to on X with B as base. This collection ബേസ് ആയിട്ട് വരുന്ന ഒരു ടോപ്പോളജി അവിടെ എക്സിസ്റ്റ് ചെയ്യുന്നു. ഓക്കെ, ദ സെക്കൻഡ് സ്റ്റേറ്റ്മെൻറ്റ് സേസ് വെൻ യു ടേക്ക് സം B1 and B2 in this collection, then you can consider B1 intersection B2. This will be like this, right? And this set can be written as union of members of B again. Okay, and the third statement says when B1 and B2, you take B1 and B2, okay, then you take B1 intersection B2, okay, now you take small element in that intersection, then what it says, suppose B1 is there, B2 is there, B1 is there, B2 is there, and their intersection, this is our intersection B1 intersection B2, and you take some X is an element in B1 intersection B2, then you can find out some B3, okay, such that B3 will be contained in their intersection B1 intersection B2. So theorem says that all these three statements are equivalent. That means one implies another one. Okay. Now we are going to prove this theorem. Okay. Proof of the theorem. The statements are equivalent. So for that we prove 1 implies 2, 2 implies 3 and 3 implies 4. 3 implies 1 and 3 implies 1. So this is we are going to prove. These are the implications we are going to prove. So first trying to prove 1 implies 2. So assume X has a topology to with B as base. What is we want to prove? We have to prove that if you take two elements B1 and B2 in script B. So take B1 comma B2 in script B. Then consider their intersection B1 intersection B2. we have to prove that this intersection can be expressed as union of members of script B itself. Okay. So before that, what is script B? It is a base for our topology too. What is a definition of a base? Base is a subcollection of tau such that every member of tau can be expressed as union of members of B. Correct? Since script B is a base for tau, script B is contained in tau itself, and every member of tau can be written as union of members of B. This is the definition of base for a topology. Now what you have, B1 and B2 are two sets in script B, and this script B is completely contained in our collection tau. So that B1 and B2 are, which implies actually B1 and B2 are belongs to tau itself, because B is contained in tau. And what is tau? Tau is a topology. Topology has the property that it is closed under finite intersection. Correct? So which implies B1 intersection B2 will belongs to tau itself, since tau is closed under finite intersection. Okay. Then as B1 intersection B2 is a member of tau. So again by this statement, every member of tau can be written as union of elements of B, implies this B1 intersection B2 also can be written as union of members of B in script B. So we get the second statement, B1 intersection B2 is union of some members of script B. So 1 implies 2 hold here. Now we are going to prove 2 implies 3. What is 2 implies 3? Assume that B1 B2 in script B implies B1 intersection B2 can be written union of, which is equal to union of B in script B. This is our assumption. What you are looking for? We are going to prove that if you take an element x in B1 intersection B2, if you take x belongs to B1 intersection B2, then there exists some B3 such that B3 is contained in this intersection. Okay? X belongs to B1 intersection B2. Okay, what is this B1 intersection B2? B1 intersection B2 is nothing but union B in B script B. So what it means, X will be belongs to some B in this union. X belongs to some B for some B in script B. Take this B as B3. B3 in script B, and B3 belongs to this union. Okay, B3 belongs to B in this union. Okay, so what you get, B3 is an element among this union, therefore B3 will be contained in this B1 intersection B2. Correct? B1 intersection B2 is union of such B's, and these every B will be clearly contained in this set also. So which implies X belongs to B3 and B3 is contained in B1 intersection B2 is clear. So we proved 2 implies 3. Next we prove 3 implies 1. So we assume the condition 3 and we will prove there is a topology tau with the B as base. Okay. So assume that if B1, B2 belongs to script B and X is an element in B1 intersection B2, then there exists B3 in B such that X belongs to B3 and B3 is contained in B1 intersection B2. This is our assumption. So we have to prove that there is a topology tau on X with B as base. For that, I am going to define a collection of subsets of capital X, and I will prove that this collection is a topology. Okay. To prove the existence of topology, I am going to define a collection. Define tau is such that collection of all G subset of X is such that having the property that for every X in G, okay, there will exist some B in B. If there exists some B in B such that X belongs to B and B is completely contained in G, that kind of elements, that kind of subsets are taking to define this topology. എന്ത് ചെയ്യുന്നു, നമുക്ക് ഒരു ടോപ്പോളജി അവിടെ ഉണ്ട് എന്നാണ് കാണിക്കേണ്ടത്. അങ്ങനെ അതിനുവേണ്ടി നമ്മളൊരു ടോപ്പോളജി അവിടെ ഉണ്ട് എന്ന് നമ്മൾ പ്രൂവ് ചെയ്യാൻ പോവുകയാണ്. അതിനുവേണ്ടി നമ്മളൊരു കളക്ഷൻ ഡിഫൈൻ ചെയ്യുന്നു. എക്സിൻ്റെ കുറച്ച് സബ്സെറ്റ്സുകളാണ് എടുത്തേക്കണേ. എങ്ങനെയുള്ള സബ്സെറ്റ്സുകളാണ്? ആ സെറ്റിലെ ഒരു സെറ്റ് നമ്മുടെ ഈ കളക്ഷനിലേക്ക് കൊണ്ടുവരണമെങ്കിൽ ആ സെറ്റിലെ ഏത് എലമെൻ്റ് എടുത്താലും ആ എലമെൻറ്റിനെ ഇൻക്ലൂഡ് ചെയ്യുന്ന കളക്ഷൻ ബിയിൽ ഒരു ബി എന്ന് പറയുന്ന ഒരു സെറ്റിനെ കാണാൻ പറ്റണം സച്ച് ദാറ്റ് ആ ബി ജിയുടെ ഉള്ളിലായിരിക്കണം. When you take an element in G, in this set G, if G belongs to tau, then what G satisfies? G has a property that when you take an element x in G, then you can find out, for every x in G, we can find out some element in script B. Script B is a collection. It has some subsets B such that B subset of x, some subsets of x. Then for every x in G, you find some element B in script B such that x will be contained in B and that B is contained in G. Okay, when G satisfies this condition for every element in it, then G belongs to our collection tau. This is the property of tau, and I am going to prove that this tau is a topology. First of all, is empty set belongs to tau? Of course, empty set has no elements. And what about the full set X? Capital X belongs to tau? If so, capital X should satisfy this condition. That means if you take any element in capital X, there should exist an element like this, correct? Okay, so I am going to prove this condition is for capital X. So take an element small x in capital X, because for every x in G we need this property. So for every x in X we have this property, we want this property. Okay, X is an element in capital X. And what do you know about script B? Script B is a collection of capital X such that script B covers X. We have script B covers X. What is the meaning of cover? Cover means when some collection can cover a set X, that set itself is contained in union of members in that collection. It is the meaning. All union of all members of script B will contain the whole set X itself. Okay, since small x is an element in capital X, small x belongs to this union, which implies small x belongs to union B, B in script B, which implies x belongs to B for some B in B. Okay, and what about this B? This B belongs to this union, correct? And the whole X is contained in the union of elements of script B, and every element in script B is also, we know that it is a subset of capital X again. So what can you say about, and this B is contained in X also. So for every X in capital X, you can find out a B such that X belongs to B and that B is completely contained in X itself. So X has this property of tau. So which implies X is a set belongs to tau. Now as a third property, we have to prove that tau is closed under arbitrary union. For that, you take collection of sets from tau. Suppose collection of G alpha are members in tau. This is an arbitrary collection, maybe finite, infinite or countable or anything. We are going to prove that union alpha G alpha belongs to tau. How will you prove this? For proving this statement, I want the property that if you take any element in this union, then there should exist an element in script B such that X belongs to that script B and B should be contained in our set union alpha G alpha. Okay, so I am taking one element, arbitrary element from union alpha G alpha now. Okay, let X belongs to union alpha G alpha. So which implies X belongs to G alpha for some alpha, because some element belongs to union means it belongs to one of the set at least for some alpha. And what is G alpha? We have G alpha is a member in tau. Then every element in G alpha has the property of tau, which implies there exists B in B such that X belongs to B and that B is contained in the set G alpha. and every G alpha is contained in union alpha G alpha, correct? Because we are considering all union of all such G alphas. So what you get now? X belongs to B and that B will be contained in union alpha G alpha. So when you take an element in union alpha G alpha, there exists B such that X belongs to B and B contained in union alpha G alpha, which implies union alpha G alpha also belongs to our topology. Now we want to prove that tau is closed under finite intersection. So last property of the topology, tau is closed under finite intersection. Okay. So I will do it for step by step. Okay. Let I take first two elements G comma H be two sets in tau. Okay. I am going to prove that G intersection H also belongs to tau. So for that I take an element from G intersection H and let X belongs to G intersection H. Okay. X belongs to G intersection H means X belongs to G and X belongs to H. And what is G? A member in tau. Every member in tau has the property that there exists some B1 in script B such that X belongs to B1 and that B1 is contained in G. Similarly, there exists B2 in B such that X belongs to B2 and that B2 is contained in H because G and H has the property of tau. By the property of tau, we will get some B1 and B2 for G and H. Okay. So which implies X belongs to B1 and X belongs to B2. So X automatically belongs to B1 intersection B2. And where this B1 intersection B2 belong to? It belongs to G intersection H. So when you take an element X in G intersection H, then G intersection, there exist elements B1 and B2 such that X belongs to B1 intersection B2 and it is contained in G intersection H. Now we are going to use our assumption 3. What was our assumption 3? Our third assumption was when you have two elements B1 by assumption 3, statement 3, assumption 3, if B1 B2 belongs to script B, B1 comma B2 belongs to script B and X is an element in B1 intersection B2, what was the assumption? Then there exists B3, correct? There exists B3 in B such that X belongs to B3 and that B3 will be contained in B1 intersection B2. This was our third assumption. So here I am going to use this assumption now. We have B1 and B2 are elements in script B and X is an element in B1 intersection B2. So therefore by this assumption we will get some B3 in script B again such that X belongs to B3 and B3 is contained in B1 intersection B2 and where this B1 intersection B2, this is clearly contained in G intersection H, which is actually contained in G intersection H. Okay. So what you get now? For every X in G intersection H, there exists some B3 such that X belongs to B3 and that B3 is contained in G intersection H. Therefore, G intersection H belongs to tau. Which implies G intersection H belongs to tau. Okay. Now we will prove that this is true for every finite intersection. If you have three elements, if G, H, K are elements in tau, then we have to prove that G intersection H intersection K belongs to tau. How will you prove this? By taking H intersection K as another set H1, you can consider this as G intersection H1. Then we have H1 belongs to tau, G belongs to tau. H1 belongs to tau by previous theorem, previous argument H intersection K belongs to tau. So you can by saying the same argument G intersection H1 is also belongs to tau. Then take H1 equal to G1 intersection H1, G intersection H1. Then what will happen? Then by similar argument we get G intersection H1. This is our claim. Okay, we get G intersection H1 belongs to tau. Continuing like this, we can prove finite intersection also true. The result is true for every finite intersection. The result is true for every finite intersection. Okay, therefore tau satisfies all the properties of a topology. Tau satisfies all the conditions or all the axioms of topology. Therefore, there exists a topology is a true statement. Therefore, we can say that 3 implies 1 is true. So, we proved all the implications from 1, 2, 3 so that the given statements are equivalent. Okay. Now, we will see one corollary of these results. Corollary says that let X be a set. Okay, X be a non-empty set and B be a collection of subsets of X which covers X. The same assumption of the previous theorem, which covers X. And suppose that also have which as property, suppose that script B is closed under finite intersection. Extra property, finite intersection, then script B is a base for a unique topology tau on X. So what the corollary says, when you have a set and a collection of subsets of X which can covers X, okay, then B also has a property that it is closed under finite intersection. That means when you take elements B1, B2, B3, etc., finitely many elements in B itself, then their intersection, B1 intersection, B2 intersection, etc., intersection Bn, where n is a finite number, is also belongs to B. This is the meaning of B has the property of finite intersection. When you take elements, finitely many elements from script B, their intersections also belongs to script B. Then this conclusion says that then script B, our collection script B is a base for a unique topology tau on X. Here also we need to prove the existence of topology on X with B as base and that topology is a unique one. Okay, we will prove this. So, for the proof, suppose B covers X. Okay, and B has this property, and B has finite intersection property. Finite intersection property. Okay. Since it is a corollary of the previous theorem, we have to use previous theorem. What was the previous theorem? Given 3 statements are equivalent. That means when you have one statement among that, you can use another statements consequently. Okay. Now, I recall the third statement of previous theorem. The third statement says that when you have B1, B2 belongs to B and you take an element X belongs to B1 intersection B2, if there exists some B3 in between X and B1 intersection B2, then we can say that this first statement is also true. That means there will exist a topology. So existence of topology will be done by if we prove the third statement of the previous theorem. Okay. Now let B1, B2 are 2 elements in script B. Then by this finite intersection property, B1 intersection B2 also belongs to script B. Okay. Now you take an element. Let X is an element in B1 intersection B2. Okay. Now let B3, I take B3 as B1 intersection B2 itself. Then what will happen? Then B3 will be belongs to script B because it is this intersection. B3 belongs to script B and X belongs to B3. B3 contained in script B1 intersection B2 is true. Correct? Take two elements B1, B2 in script B and take an element X belongs to B1 intersection B2. Since B has the property, it is closed under finite intersection property, B1 intersection B2 belongs to B itself. So I name B1 intersection B2 as B3. Then B3 belongs to script B is true, X belongs to B3 is true and B3 contained in B1 intersection B2 is true. So what is this says? This is the third statement of the previous theorem. Okay. Therefore by previous theorem, we can use 3 in place 1. Here it is 3 is true, then 1 is also true. Correct? Therefore, by previous theorem, there will exist a topology with B as base. So, we can easily prove the existence of topology here. So, therefore, by previous theorem, there exists a topology tau on X with B as base. B as base. Okay. So we get the existence of the topology. Now we have to prove the uniqueness of the topology because corollary says that there exists a unique topology as B as base with B as base. So let us assume there exists one more topology with B as base. Suppose tau1 is a topology on X with the same property, that means with the B as base. Then what will happen? This tau1 is actually another topology, okay, which is different from tau. Then we already proved that when two topologies on a same set X has the same base, then that topology will coincide. Since two topologies with the same base, with the common base is always equal, always same or equal. Therefore, tau1 will be equivalent to tau, which implies there exists unique topology on X with B as base. So, which proves the corollary.